So we learned last year that F is equal to ma, meaning that forces cause a change in linear motion, or forces cause a linear acceleration. In the same way, a force can also be used to produce rotational motion or changes in rotational motion. But in this case, we use the term torque. Torque is not just force, it's where the force is located or applied as well. So torques cause a change in rotational motion in the same way that just a plain force causes a change in linear motion. When we think about the calculation of torque, we pay attention to, again, where that force is being applied. The term R is used to represent the distance from the fulcrum or the pivot, so wherever the rotation is about, and then the force, of course, is F. Now, it's not just the amount of force and where it's applied, it also involves the angle between those two things. So the official formula for torque is written like this. That's right off of your formula sheet. The torque vector is equal to the r vector, the moment arm, crossed, how that's pronounced, crossed with the force vector. This x here is referred to as a cross product. What we're doing here is we are taking the size of r and the size of f, but we are making sure that we only include the part of those two vectors that are perpendicular to each other. So torque can also be written as r times f perpendicular, or the way that we generally look at it is r times f times the sine of the angle between the two vectors. Now, if the force is applied perpendicularly, it's going to be most effective, and you naturally see a lot of situations where that occurs. But if there is some sort of an angle between r and f, we have to take that into account using the sine of that angle. Let's take a look at some examples. So this is a pretty straightforward example where we have a force of 20 newtons being applied at 1 meter from the pivot point. That would be a torque of 20 newton meters, or tau, that's the symbol for torque, equals 20 newton meters. Now that's actually only the magnitude of tau. We're going to get to that in a second as to how to find the direction as well. The other force here is smaller, actually half as small, but it is at a distance that is twice as big, 2 meters away. And so again, our torque would be 20 newton meters. They are perpendicular, both of these forces are perpendicular to the beam, so we don't need to worry about that angle. Let's look at an example where we do need to worry about the angle. So this stick or this beam, whatever it happens to be here, is being rotated about point P. The forces that are causing that rotation are a 50 Newton force and a 10 Newton force. Now the 10 Newton force, the torque due to that force, is not going to be that hard to calculate because of the perpendicular orientation of the two things, the R and the F. But the 50 Newton force is a little bit more complex. It's going to involve a little bit of trigonometry. Let's take a look. All right, so again, let's calculate the magnitude of the torque. So officially, this is how we would write that. So the torque is a vector quantity. It has a direction to it. Again, we'll get to that in just a second. And those vertical lines indicate the magnitude or the overall size of the torque. So we would calculate this by taking the distance of 0.5 meters. That's the distance from the pivot point, that's been marked P here, to where the force of 10 newtons is being applied. Then we'd include 10 newtons for the force. And then if we want to be really official, we would put in the sine of 90 degrees. Okay, that is the angle between the 0.5 meter long R and the 10 Newton force. But the sine of 90 is 1, and so if we see it's perpendicular, a lot of times we just sort of drop that entirely. Okay, if we look at the magnitude of the other torque, the torque caused by the 50 Newton force, we would use as our R value here 0.2 meters, because that's the distance from the pivot to where the force is applied. And then we would use the 50 newtons. And then we'd have to think about this angle. So there's actually two ways of thinking about it, but we can see them both if we just sort of sketch in some reference lines. So the moment arm is along this direction, and the force is along this direction. And so that forms two different angles. There's an angle here and an angle here. And the sign of both of those angles are at exactly the same. So this larger obtuse angle, 90 plus 60, that would be the sine of 150 degrees. If instead we grab this angle up here, that would be 90 minus 60, or 30 degrees. And you can check that on your calculator. It does come out to be the same value of, I think it's 0.5 here. Either way, both of these calculations, as it turns out, come out to be 5 Newton meters. So tau for both of these is the same. So the same, or I'm sorry, a different force can be applied at two different locations, maybe with an angle, and it is possible to get the same amount of torque, or the same result from that force. Now, torque is not always produced by an applied force. These situations both involve gravity as a force that applies a torque. In this top picture, not only do we have this black weight exerting a downward force due to its weight that could be used to calculate torque about the pivot, but we actually also have the weight of the meter stick itself. So the meter stick itself, of course, its mass is all along the stick. Where do we choose the weight to be? Where's the arrow going to be labeled? Well, it could be labeled at every single point, but how would we ever calculate that? It turns out that if we find the mathematical average of all those points, meaning the location of the center of mass, that can be the place where we locate center of mass, where we locate the weight. So the weight is truly spread out across the whole stick, but mathematically, if we locate the weight at the center of mass, we will be able to correctly calculate torque. So in that case, we would take the R times the F here. For the force being applied by the string, this would be our R value, this would be our force, always along the direction of the string, and in this case we would need to use the angle. Here's another just kind of a fun example of how torque can cause rotation. So this ball that's going down a hill, it is an inflatable human hamster ball. But the weight, again, would be at its center of mass, would be right here. Of course, it's completely spread out across that ball, but we would locate it at the center of mass for the purpose of our calculations and our analysis. And that is away from the pivot point. And so it would cause the ball to rotate like this, and of course to roll down the hill. All right, torque also has a direction to it. It is a vector. To find that, you need to use your right hand. Make sure it's the right hand. And let's just kind of quickly look at how this would look in this situation we just discussed. So for the black mass, R would be in this direction, so you would point your fingers that way. And then F would point down. In order to do that, in order to curve your fingers in that downward direction, you'd have to rotate your hand completely around, and that would cause your thumb to point into the page. Okay, if it's into the page, you could symbolize it this way, like we did when we studied magnetism in our first year course. But the key thing is to notice that it does point into the page. As opposed to the string, okay, the string is being, or the spring scale is being applied right here. So this is my R vector, and this is my F vector. And if I pull my fingers in the direction of R and then curl them in the direction of F, that causes my thumb to point out of the page. A lot of times people consider that to be the positive direction. You could symbolize it like this, but in our calculations it'll be important to consider this red torque to be maybe negative and the blue torque to be positive, so that we get our calculation set up correctly. There is a follow-up video that shows an example of how to calculate net torque. The key thing with net torque is that you have to pay attention to those inward and outward directions as you calculate the total amount of torque acting on a system.